Hello everyone. Today we're in tutorial 4, first year university physics, static equilibrium. Okay, let's go to my notes.
Static equilibrium. There are two conditions that are required for static equilibrium. The first condition comes in two forms. There are two related conditions. Net force at a point is zero, hence the forces or components of forces in the x direction are zero. The sum of all the y forces or y components of a force are zero. The sum of the Fz forces or Fz components of a force are also zero. These are all applied at a single point. I'll be showing you this on the whiteboard in more detail. The second form of the first condition is that the net force in the whole system is zero. So if you add up all the forces in the x direction or the components of the force in the x direction, similarly all the forces or components of forces in the y direction, the forces or components of forces in the z direction, they must all be zero. And this can be applied to all the forces of the whole system. The second condition requires torque, because even if these conditions are satisfied, it doesn't mean that you have equilibrium, because there are turning forces as well. And a turning force is called a torque. So before this, I need to maybe define torque for you, although I'm going to define torque again when we do rotational motion, but we need it now. So I'll end up repeating the definition, which won't hurt. Anyway, torque is a turning force defined as follows. Essentially, you apply a force, you have an axis of rotation. You always take the perpendicular distance of the force from the axis of rotation. So if I take the line passing through the axis of rotation perpendicular to the line of action of the force F, that's this line. This is the line of action of force F. The line of action is just a line that goes through the force. This is my direction of the force, so we have a perpendicular distance. So this formula applies strictly to this force multiplied by the perpendicular distance from the axis of rotation. When a force is acting at some angle to a line that passes through the axis of rotation, you have to take the perpendicular component of the force to obtain the correct torque. So the torque in this case is given by the perpendicular component to the line passing through the axis of rotation. And r is the distance to the point of action of the force. So the formula then becomes this, and we see from our normal way of resolving vectors that F perpendicular is the opposite. So the formula becomes F sine theta r. Now there's a much better way of doing this. Instead of taking the perpendicular component, I can take the line of action of the force, and then I take the perpendicular distance from the line of action. This is what I've done here. It's easy to prove that the two things are equivalent. Since these angles are opposite, they're equal. So you'll see that F sine theta gives you this component of force, and here R sine theta gives you this perpendicular distance of the line of action of the force. And so you can see when you put it into the formula, you have the same formula. So when you have a force acting in a certain place, take the line of action of the force, and then you take the perpendicular distance from the axis of rotation. And that gives us this formula. So there are two ways of dealing with force which is at an angle like this. Either take the perpendicular component, or better, much better, take the line of action of the force and then take the distance from the axis of rotation. So this defines my torque. The units of torque, again, they're going to be found from the formula. Force in newtons, R in meters, in base SI units. So the units of torque are Newton meters. I've included a general definition. Now, the general definition of torque requires a vector operation called the cross product. Torque then is here a vector. In the work that you're going to do, you don't need this general definition, and you don't have to worry about torque being a vector. You just need to understand it as a turning force. In other words, the definitions above are all that you need. I'm including this for those of you that have an interest and those that may go on to do physics at a later time. So the proper definition is that torque is R cross F. Now the definition of the cross product is the magnitude of the vectors multiplied by the sine of the angle between them. So I extend the line of action of R, and this is the angle between the two vectors. Now the direction of the torque is given by the unit vector. And this unit vector is perpendicular to the plane that contains R and F. And its direction is given by the right-hand rule, which I'll show you below. So I'll show you my notes. I won't go through this in any more detail because it's not something that you will need at your first year level. I've just included it for additional interest and reference, especially for later time. So this is the general definition, which again you won't have to worry about for your first year work. Now we come to the second condition. Objects in the system may move even if the first condition is satisfied. This happens when the sum of torques are not zero. Before stating the second condition, we must define the signs of counterclockwise and clockwise torques. Which ones are assigned positive or negative signs is a matter of convention. We will adopt the following convention. It doesn't really matter whether you attach a minus sign to the clockwise or the anti-clockwise torques. Anti-clockwise is another word for counterclockwise. Torques that produce a counterclockwise, this is the abbreviation, counterclockwise rotation about the axis of rotation will be assigned a positive value. These torques will be labeled TAC. Torques that produce a clockwise rotation will be assigned a negative value, and these torques will be labeled tau C. This is the letter tau, by the way, the Greek letter tau. So once we've adopted a convention, we can state the second condition as follows. The algebraic sum of clockwise and counterclockwise torques must be zero. To apply this condition, any axis of rotation can be chosen. Problems are simplified if the axis of rotation is chosen to lie on the line of action of the most unknown forces, possibly also an unknown angle. If not so chosen, it may not be possible to solve the problem. You're free to choose the axis of rotation wherever you want, but if you choose it at the place where you're finding unknown forces, unknown forces may be in more than one point. So you choose the axis of rotation to go through the place where the most unknowns are, including if the angle is not known. You'll understand this better when we do examples. And you'll see how to use this again when we do examples. I have some common problems which I'll outline, but before I do that, let me go to the whiteboard to go through some of these conditions on the whiteboard. Okay, this is my diagram. We're going to start by looking at the application of condition number 1 for static equilibrium, when we're going to apply at a point. Here I can think of a point, or I can think of block A. So let's look at all the forces that are acting. Let's look at block A. There's the weight of the block acting downwards. I might as well draw this. The weight of the block B acting downwards, and C acting downwards. So this W1, W2, W3. Now, an important point is that these pulleys are frictionless and massless, and the string is uniform, or equivalently, another word for uniform is homogeneous, meaning the properties are the same throughout. In this case, the tension is going to be the same throughout. So, even intuitively, in order for A to be balanced, we have to have an equal and opposite force T1. I can also obtain this relationship by the application of condition 1 to block A, which I will do later. Similarly here, I have to have a force, a tension T2 to balance W2. And here a force T3 to balance W3, equal and opposite. Now, my tension is the same throughout, so at this point, which I'll call point B, this string pulls on this point with a tension T1. Oh, let me try and draw better than that. On this side. I'll explain this later. I'm anticipating. I'm drawing this. I can draw my tension T1 there. We call this angle theta. And this angle phi. Let me do that better than that. This is again, the string is uniform or homogeneous, pulley is frictionless, so my tension here will be T3. So these are all my forces that are acting. I'll come to this bit later. For now, I'm going to apply condition 1 to block A, or if you like, you can put a point there, and I'm applying it to this point, to point A. So apply first condition for static equilibrium to block A. You can see there are no forces in the x direction, so this is equal to 0. The forces in the y direction is T1 and W1. Now T1 is in the positive direction. I've defined the directions at the top here. This is positive, this is in the negative direction, so T1 minus W1 equals 0. So we get what we know by intuition. To balance, these two forces must be equal and opposite. Apply first condition to block B. Similarly, the x forces there are no x forces, so that's just 0. The sum of the y forces, positive direction, negative direction, equals 0, from which we get T2 equals W2. And you can see the next step is to apply to block 3. All of this we can get just by intuition, that we know the force is balanced. Again, there are no x forces. My sum of the y forces, T3 in the positive direction, W3 in the negative direction, equals 0. So I get T3 equals W3. Although it's obvious, let me write it up here. Okay, and now let me erase this. The next thing I want to do is to apply condition 1 now to a single point. In order to get static equilibrium, all the forces here must balance. So let me erase all of that. So I'm going to apply now to point B. Now in all these cases, in order to apply the first condition to a point, I must resolve my forces at angles into the vertical and horizontal parts. So let me resolve T1. As always, make T1 the diagonal of a rectangle and the sides of the components. And always notice the tails join together and the arrows point away from the tails. I think I'm going to draw that in a different color. Let me draw that again in orange. Right, so this is T1, this is the adjacent. So this is T1 cos theta. And this one is the opposite over here. So this is T1 sine theta. This side, T3, again the diagonal of a rectangle. Again, the tails joint, the arrows point away from each other. So this one now is T3 sine phi. The adjacent, T3 cos phi. So the sum of the x forces and the sum of the y forces must equal 0. So let's do the sum of f of x first. This is in the positive direction. T3 cos phi minus T1 cos theta equals 0. So I get my relationship. In an actual problem, you'll be given data, so you'll make the appropriate things the subject and put your numbers in to get your answers. But here I'm just showing you how to apply to obtain the relationships. So we're not going to put in numbers. We'll have examples of this in the tutorial sheet. So we have T3 cos phi equals T1 cos theta. Now my sum of Fy this time I've got two forces in the positive direction, T1 sine theta plus T3 sine phi, and the force in my negative direction is W2, which translates to T2. So this is, theta is in the negative direction here, so this is minus T2 equals 0, and we have, making T2 the subject, T2 equals T1 sine theta plus T3 sine phi. So I'm just going to check that I've got everything right. Okay, after 3. 1, 2, 3. Just to make a few points about the forces acting here in action and reaction. The way we look at the tensions is this. This point here is pulling on block A with a tension T1 to balance W1. By action and reaction, block A is pulling on point B with tension T1. And similarly, when we look at block B, point B is pulling on block B with tension T2 so that it balances W2. Similarly, block B is pulling on point B with a tension T2 by action and reaction. And similarly here, by action and reaction. Point B is pulling on block C with a tension T3 in order to balance W3. And similarly, block C is pulling on point B with a tension T3. So this is how we get the forces acting. And then we can apply my first condition. Right. This is an example where we've applied the first condition to a single point. Even here, we can think of block A as a single point. So I'm going to move on to another example where we apply the first condition for static equilibrium to the whole system. It's not always appropriate to apply it to points. There are certain problems where the forces are acting at different points, but yet overall static equilibrium is achieved. So that's our next example. Again, we'll continue with the first condition, but this time we'll apply to the whole system. And suppose I've got a bar which hangs from hanging from the ceiling. I've got its weight, let me call this weight W, and I've got the tensions in the string which are holding this up. Again, in all of this, I resolve the forces horizontally and vertically. If this is tension T1, this is tension T2, call this theta, call this phi, this will be T1, this will be T1 cos phi, this will be T1 sin phi, this will be T2 cos theta, this one will be T2 sin theta. Now the second condition applies to the whole system. So the sum of the f of x forces must be 0 for static equilibrium. But this time I'm not looking at the forces at a point. I'm looking at the forces on the whole system. The only two horizontal forces are these. Again, if I define plus y minus y plus x minus x, this one's in the positive direction, this one's in the negative direction. So I've got t1 cos phi minus t2 cos theta equals 0. My Fy condition equals 0. These are the two vertical forces, T2 sine theta and T1 sine phi, and these must balance the weight W. W is in the negative direction. So here, this one I'll need a bit more room. So T2 sine theta plus T1 sine phi minus W equals 0. I can then use these equations to get a solution. Though often, only in very simple problems will this condition be sufficient. More generally, I'm going to need the second condition to solve a problem. So let's have a look at the second condition. Now the second condition is the sum of torques in the counterclockwise and clockwise directions must be 0. And we define clockwise torques, anti-clockwise torques, or counterclockwise, depending on which term you like. And the clockwise torques are negative. So these torques should also be 0. So that's my second condition. For this one, the best way of seeing this is through a specific example. So I think I'm going to show you this when I come to show you some typical problems. So I think I will leave this for now and explain it to you by way of the general problems. So let us go to the notes. We'll be doing a lot of examples in the tutorials anyway, where I'll show you how these conditions work. But this is a typical problem then. This is a ladder resting against the wall. We assume the wall is frictionless, but the floor is not. And it's the friction in the floor which stops the ladder from slipping. We've got the weight of the ladder that acts, and we've got the normal reaction of the ladder on the floor, and the normal reaction of the ladder resting against the wall. So these are the forces that are acting. And typically I'm giving the length. But when I come to calculate torques, I have to take as we said, the perpendicular distance of the line of action of the forces from the axis of rotation. Now, again, it's very common to choose the axis of rotation to be 0.1. This is because we don't know theta, usually. It really depends on the question, but typically it's better to choose for a ladder to choose the axis of rotation at this point. There'll be an example in your tutorials which I can explain this better when we've got actual information. So you can see what data we have and what data we don't have. But you always try and choose your axis of rotation through a point of the most unknown quantities. Okay, I'll show you all of this in the whiteboard. These are my first conditions. Apply the first condition to the whole system. Again, this is an example where it's better to apply to the whole system, not to individual points. The second condition with the sum of torques being 0. So this one. The rest is just going through the equations. By doing this, I can obtain a formula for the frictional force. So in this example, it's basically to derive a formula for the frictional force. But in an actual problem, it depends what information you're given, what it is you're asked to find. In the last thing, before I go to the whiteboard, in a problem where you have a boom, for example, resting against the wall, it's being held up maybe by a rope, whatever. The only point I want to make here is that when you calculate the forces that the wall exerts on the hinge connecting the beam or the boom to a wall, the resultant force is not necessarily along the beam or sometimes they call this thing a boom. But the resultant force of the wall on the boom or the beam need not be parallel to the beam. Just make a note of that. But when you do the calculation, you see that it doesn't happen. And you will see that in a later example. Okay, so now let me go to the whiteboard to see some of the features of this. Okay, let me see if I can draw this nice and big. I'll try that again. Again, not very good. A bit better. This is my angle theta. Now I've got a ladder resting against the wall. This wall is frictionless. The floor has friction. It's the friction which holds the ladder or stops it from slipping. So then I've got a frictional force acting here. Now I've got the weight of the ladder acting downwards, and the weight will act through the center of mass, and if the ladder is uniform, this will be halfway down. If we take the ladder to be of length L, this point will be at L over 2, call this W, which equals mg. Now my only other forces that act are the normal reactions. There's a normal reaction here. I'm going to call this point 1, and I'm going to call this point 2. So this normal reaction is N1, and this normal reaction is N2. These are my only forces, my two normal reactions, my weight, and my frictional force. This of course is a right angle. My aim is to calculate friction in this example. In the course of doing that is to show you how to apply conditions 1 and 2. In this kind of problem, we apply condition 1 to the whole system. So let's start by applying condition 1. Or first condition. So first of all, I do the sum of the horizontal forces and sum of the sum of f of x equals 0. My only horizontal forces is this one and this one. Now I'm going to define my positive and negative directions. Minus x plus y minus y. So this is in the positive direction, and my frictional force is in the negative direction. These are the only two forces acting. Minus F equals 0, which implies that N2 equals F. This will be my equation 1. Then I consider the forces in the y direction must equal 0. Again, applied to the whole system. I look at all my vertical forces. So this is in the positive vertical direction, the negative vertical direction. So this one is N1 minus mg equals 0, which implies that N1 equals mg. This is my equation 2. Now apply second condition. So I need the sum of the anti-clockwise or clockwise torques, the sum of the clockwise torques. Now, in order to determine the torques, I need to draw the lines of action of the forces, and I need to choose the axis of rotation. The first job then is to choose the axis of rotation. Now, here you've got a number of forces acting, and the problem, it depends on what things you're given, but you try and choose the axis of rotation through the most unknown forces. Since I'm not given any forces here, I'm going to pick this as my axis of rotation because it contains so many quantities. It has F, it has theta, it has N1. And this, by choosing it like this, it will simplify the calculation. But now I need the perpendicular distance of from the lines of action of the forces. Now, let me take this one and draw its line of action. The line of action just passes, I'm not worrying about the direction right now, just the line of action. Now I want the perpendicular distance of the line of action from the axis of rotation, which is this distance. So for this force, it's this distance. We call this x. Now, if I call this whole length L, then from here to here is L over 2. So this becomes L over 2 cos theta. So my x is L over 2 cos theta. So this one then is my counterclockwise or anti-clockwise. So I've got this force multiplied by this distance. So I have mg L over 2 cos theta. Now so this should be a C here, look. Let me rub that out. This is clockwise. So now for my clockwise torque. Okay, so I've got this force now. Now this force is tending to pull this way, so this one is clockwise. Now I need its line of action first. So let me draw the line of action. And I want the perpendicular distance from the line of action to the axis of rotation. So that's this whole distance. You can see that this distance is y. And we can see that y is equal to, the hypotenuse is L. This is the opposite. So this is L sine theta. So my torque here becomes this distance multiplied by this force. So this becomes N2 L sine theta. But N2 is equal to F L sine theta. This is my equation 3. Let me see how much I can squeeze in. Now the condition is my anti-clockwise are the positive ones, minus according to the convention I chose. You can choose the opposite convention, it really doesn't matter. Will I have enough room? mg L over 2 cos theta minus F. This is in the negative direction. So if you find this to be negative according to my convention, this is FL sine theta, and all of this equals 0. Let me continue this equation up here. Let me keep my equations 1 and 2, and let me erase this bit. So let me rearrange this equation. Since this is equal to 0, I can write this up here. Well, let me rub a bit more out. So I have mg L over 2 cos theta equals, take this across the equal sign, I have f L sine theta. I can see that my L's cancel. I want to make f the subject. So I have mg cos theta over 2 sine theta. Now I know that my tangent is defined as, let me do it for you over here, tan theta equals sine theta over cos theta. So this one is going to be 1 over tan. So let me put f this side and write this equation on this side. So cos theta over sine theta is tan, so this is 2 tan theta. And so this gives me my formula for the frictional force. Not all the problems will ask you to find the frictional force, it depends on the problem. I've used this example, one, because it's a typical example of a ladder against the wall, and then you're given certain data to calculate. But it was quite nice to derive an expression for the friction, and to show you, using the example, how to apply conditions 1 and 2 for static equilibrium. Okay, that's this example. Let me make sure you have all the bits so you can go through it yourselves as well as the stuff on the whiteboard. So that's that bit. And then the final bit where I get my formula, f equals mg over 2 tan theta. And this was the last bit which I explained. Again, let me make sure you have it. Okay, I think that's enough for today, so let me stop there. And okay, let me say bye-bye.